In this video, I wanted to explore the relationship between the derivative of e to the x and the derivative of ln x, which we have derived in this lecture series. So just to recap, I'm sorry while I scroll to on my tablet. If g of x is e to the x, its derivative g prime of x is always the same thing. The derivative of e to the x is always itself. And if f of x is our function ln of x, its derivative function is 1 over x, the reciprocal function. And what I wanted to explore is how does this come back to slope and the idea that e to the x and ln of x are inverse functions. So looking back at the graph of e to the x and ln of x, in class we talked about the graph of e to the x is an exponential function. They always look like this. They grow really, really rapidly as x goes to infinity, and they get very, very small, or they head towards 0 when x goes to minus infinity. ln of x, since it's the inverse function, will have exactly the inverse points. There's the symmetry about the line y is equal to x, which is always a present algebraic feature of inverse functions, but basically ln functions have this shape. As it goes to infinity, ln goes to infinity, and as x approaches 0, ln of x heads to negative infinity. And this is actually a useful limit to remember, which can sometimes appear on occasion, but the limit as x approaches 0 from the right of ln of x is equal to minus infinity, which can be seen by the fact that this graph will continue down negatively asymptotically. Basically, just like in some of those other functions, it can get infinitely small. And I mean, really, the reason that works is because, anyways, I'm getting off topic, not important for this video. What I wanted to explore is, let's say we were looking at functions and their derivatives and their values. Does it make sense? So let's say we're looking at, what about f of 1 or f of 0 and so forth. But like, say for example, with f of 1, that would be the x-intercept for the logarithmic function. So f of 1 here, since f of x was equal to ln of x, f of 1 would be equal to the natural log of 1. And if you remember, log of 1 is always 0. Because anything to the 0 power, e to the 0 power makes 1. So that's the solution of this. Or again, you could use a calculator to confirm. But we don't want to rely too much on our calculator if we can use our brain instead. So cool. Okay, what is my point here? But let's say we were looking at the symmetric point on e to the x, which would be g of 0. So g of x, we'd said to let be equal to e to the x. What about g of 0? That would be e to the 0, which is of course 1. That's, again, these are inverse inputs to the function, and those are the symmetric points. Again, I'm getting into a lot of algebra right now. Sorry, if it's been a while since you had algebra. I'm not trying to focus too much on that. But what I wanted to mention is what is the slope at these points, and it should be symmetric. The symmetry means that the slope should be the same. Well, it's at this particular point. If looking at other points, this slope will actually be the reciprocal slope, or not true reciprocal, but it depends on the points. Anyways, obviously we can use derivatives to find the slope. That's the whole point of the derivative. The derivative function gives us the slope at a particular point in time. So, as we know, f prime of x is equal to 1 over x. And g prime of x is equal to e to the x. The derivative of e is always itself. So let's say we wanted to know what is the slope of e to the x at 0. That would be the same exact thing. E to the 0 is 1. And basically what we'd have is the slope at the y-intercept of e to the x is 1. And actually, if you look at it, notice that seems approximately correct. Because if we were to draw a straight line with slope of 1, it would rise over run of 1, and it appears to be the proper tangent slope to the tangent line at that point. And if you go, notice we get a slope of 1, not a coincidental point. And this is something I said earlier, is that the evaluation of e to the x is the same as its slope, meaning that at this point in time, the slope will be the same as its value. So here, the slope will be 1. If you go over here, say for example at 2, the slope is 2, the slope is 3, the slope is 4. Every point where it intersects with that y value it will always have that slope. Notice, and if you think about e, as you move to the right, sorry, my mic is back, or my video is appearing backwards. As we move to the right on e to the x, the slope actually gets steeper and steeper and steeper. That slope is equal to the value, and it makes sense. This kind of makes sense with the graph, because as you go to the right, steeper, 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 it's equal to its value. Anyways, well, what about over here? Since, notice, due to the symmetry, we'd expect the slope to be 1 here as well, because it's an inverse function, and again, it must exhibit this particular type of symmetry. But notice, appears to have the same slope, and it does. Let's check it out. So if we were to do the same point, this would be the location when x is equal to 1 on f of x, right? Because that would be right there. And this one I'm calling f, that one I'm calling g. So the question is, what is f prime of 1? Well, notice since the derivative of ln is the reciprocal function, I'll plug that in. 1 over 1 is 1. And notice it works out. The slope is also 1, so it makes sense. And that's just kind of what I wanted to explore in this video. Or say, for example, we wanted to know, well, what about at f of 2? What's going on over there? That would be the ln of 2, which is related to doubling time of it, but it comes out to be approximately 0.69. And if we wanted to know, well, what is the slope there, we can use the reciprocal function. F prime of 2 would be 1/2. And basically, again, because it's 1 over x, if we move over here to the point at 2, this will have a slope of 1/2 instead. And as you keep moving to the right, it'll be 1/3, 1/4, and so on. The reciprocal function, the ln function, as you move along the curve, imagine, and if you kind of imagine the slope here as at 1. Try to draw this. Let me try to show you with my hand here. And as I move to the right, it's kind of flattening out. But basically, every increment that you move to the right, the slope is getting the respective fraction, 1/2, 1/3, 1/4, 1/5. Kind of interesting property of the ln. And again, it seems about right. It's gradualizing, and you can imagine why, the importance of these functions and their relationships together. That's enough going into this, but it can kind of seem strange that ln of x has such a simple reciprocal function slope, and it doesn't really seem to relate to e to the x, but at the end of the day, hopefully this makes a little bit of sense. And again, most important thing to remember is, what are your derivatives? So, because if we know our derivatives, we can always figure out slopes at any point in time. E to the x is itself, ln of x derivative is 1 over x.